Okay, all right. Well, it's a real pleasure to have Sarah Wellons here today. She is a graduate student at CfA, Center for Astrophysics, and she's a fifth year, and she came there from Princeton. And this is her first time in Texas, so hopefully we'll make her very welcome. She will be here all today and tomorrow, and so if you haven't gotten on her schedule yet and have some time, definitely feel free to add yourself to her schedule. And today she'll be telling us about the theoretical background and predictions and simulations for galaxy evolution. So thank you, Sarah.
Thank you, Pete. Shouldn't we all say howdy first? Howdy. Welcome.
Thank you. So I'm a grad student at the CfA working in Lars Hörnquist's group. Our group has this big cosmological simulation called Elliptical. It's a cosmological hydrodynamical simulation, which means that we have thousands of galaxies forming and evolving in this cosmological context. And I have been in particular studying these type of galaxies called compact ellipticals, which are very common at high redshift, less common in the local universe, and trying to figure out how these types of galaxies form and evolve within the simulation. And the results that I'll show you also have some broader implications for methods that we use to track galaxy populations observationally. So I'll get into that a little bit at the end. But first of all, I want to just tell you a little bit about these galaxies, compact quiescent galaxies. What you're looking at here is a set of distributions of galaxy sizes at different redshifts going left and right. So redshift 0 is over there on the left, and at different stellar masses going up and down. It's further broken down in each panel into star-forming galaxies in blue and quiescent galaxies in red. So if we look around here, around 10 to the 11 solar masses, around redshift 2, you can see that there's this population of quiescent galaxies which have typical sizes of about 1 or 2 kpc, which is very small, in fact. These are some images of what they look like taken with HST, so you can see why galaxies like this are referred to as red nuggets sometimes. So you'll notice that there's a big disparity in the typical size of a star-forming galaxy and a quiescent galaxy, and if you track where the peak of this histogram is, forward to low redshift, you can see there's a very strong evolution in the typical size of a quiescent galaxy. So the presence of these galaxies at high redshift has prompted a lot of questions. For example, how do galaxies like this actually form? How do you form something that dense and that massive? Why do they form with such small sizes? Where are all the star-forming compact galaxies? Because presumably quiescent compact galaxies come from star-forming compact galaxies. And where do they go? What happens to them at low redshift? And why don't we find them in the same abundance in the local universe as we do at high redshift? Now, I'm going to be approaching this question in the context of the Elliptical simulation. This is as I said, a cosmological hydrodynamical simulation. It's a periodic box of about 100 megaparsecs on the side, which is initialized in the very early universe with both dark matter and baryons and evolved forward to the present day. So there's a lot of physics that you need to put into the simulation, not only n-body for gravity, but also a treatment of hydrodynamics. For this, we use the moving mesh code AREPO, plus phenomenological models for all the physics that one needs in order to form realistic galaxies, like how gas cools to form stars, how those stars evolve over time and feed back into their environments through supernovae and stellar winds, and how supermassive black holes accrete and feed back into their environments as well. This image that I'm showing here shows a slice through the simulation volume at redshift 0 with the dark matter structure here on the left transitioning over into the gas, the structure of the gas on the right. So you can see that we have all of these different layers on top of each other evolving together. And I'm going to show you a movie here that will, just for context, show you what the simulation looks like. This is going to be the same sort of slice at redshift 0. We're going to zoom in and out, and it's going to flash through a couple of quantities along the way. So here we're starting at the largest scale with the dark matter structure. You can see the periodicity with some repeated features on either side of the box. We're zooming into a big cluster. We're going to gas temperature now, with red being hot gas and yellow being slightly cooler gas. So all these yellow dots here are going to be where gas is cooling to form stars and galaxies. This is now gas metallicity. You can see some high metallicity outflows, for example, from some of these galaxies. And we're now moving into the stellar light. So this is what we might see if we were to observe the galaxies in the simulation. And we're zooming in now on a nice spiral galaxy. So this galaxy, you can see it's young, it's sort of blue looking. And as we zoom back out, it's going to switch into the gas density, with blue and white being high gas density. So you can see it's got a nice rich disk of cold gas forming stars. And again, all of these little points of blue and white are where the cold gas is, where the galaxies are. So you can get a sense for how many galaxies there are in the simulation. There are thousands, tens of thousands, in fact. And this is what makes the simulation very useful for the problem that I want to solve, which is the question of these compact quiescent galaxies. This is gas velocity now. This is just a cool picture, I think. And now we're going back out to the dark matter density. So because there are so many galaxies within this cosmological volume, even though the types of galaxies that I'm interested in are somewhat rare, just the fact that there are so many galaxies ensures that I'm going to get a decent sized sample of them. And so you can actually pick them out of the simulation and trace them back and forth in time and ask what makes these galaxies different and how do they form and evolve within this cosmological setting. So I'm going to show you a sample of galaxies now that exist within the simulation at redshift 2. All of the galaxies that I'm going to show you are around the same stellar mass, a few times 10 to the 11 solar masses. Here are some images of some nice extended spiral galaxies with the half mass radius here in the lower left-hand corner. Half mass radius in this case means the radius of the sphere that encloses half of the stellar mass that is bound to the galaxy. So in addition to extended spiral galaxies like this, we also see galaxies that look more like this, which have the same amount of stellar mass as the galaxies on the left, but pack it all into a much smaller region of space. And these, of course, are the types of galaxies that I'm interested in. These are the compact elliptical galaxies. And you can see that, in fact, they have much smaller half-mass radii, just 1 or 2 kpc. We can also ask, what might galaxies like this look like if we were to observe them? So these are now mock observations of the galaxies on the right here, where essentially what we have done is to take the SEDs of the star particles that comprise the galaxy, redshift them to 2, integrate over the HST bands, and bin them into pixels. And you get some of, and apply the PSF, and you get some approximation of what that might look like. And if I, yeah.
Sorry, if I get the, as maybe it says, the half-life radii go down like quite a bit.
Right, okay. You mean between here?
Yeah, one's half mass, one's
So
half light.
this is a 3-dimensional half mass radius. This is the effective radius that I measured off of these postage stamps.
Okay.
So part of it is projection.
Yeah.
You'll get smaller radii over here just because of projection. And the other part is that this now is a measurement rather than an actual physical reality. Yeah. So there's some uncertainty there. Yes, good eye. So now I'm bringing back on this side of the figure the same images that I showed you at the beginning. These are real observations of compact galaxies. And so at least by eye, they look like pretty good analogs to the observed galaxies. And this gives us some confidence that if we find out how galaxies like this are forming and evolving in the simulation, it might tell us something about how galaxies like this are forming and evolving in the real universe. All right, let me quantify a little bit what I mean when I say compact. So for this part of the talk, when I'm talking about compactness, I'm making a selection on the mass size plane, which is what is shown here. These are all the galaxies in the simulation at redshift 2 that have stellar masses of at least 10 to the 10. And I make 2 cuts here to select my compact population. First, I want massive galaxies, so I select 4 stellar masses of at least 10 to the 11. And of course, I also want them to be small. So half mass radii of 2 kpc or below. And then this quadrant of the mass size plane is what I'm referring to when I say compact. And when I make this selection, I get a sample of 14 of these massive compact galaxies, which I'm going to look at in detail and trace around with the simulation. Now, when I make this selection solely based off of mass and size, as a side effect, I'm also picking galaxies which are preferentially quenched at redshift 2. This is the specific star formation rate against stellar mass, again at redshift 2. Here's the star forming main sequence. And so you can see about 2/3 of these galaxies have fallen off the main sequence by redshift 2 and would be quiescent, which again sort of harkens back to the observations. Yeah.
Go back. I can't quite tell. So do you have extended galaxies in there?
Right, well, so each of these little orange points here
Yeah.
are off the main sequence, and they're not in my compact sample, so they have larger sizes.
So you do this. Okay.
Yeah. All right, so each of these galaxies I have traced back to higher redshift to find out how they formed and what drove them into this quadrant of the mass-size plane. When I looked at all of these in detail, I saw two formation mechanisms that characterize their evolution. I'm going to walk you through two specific examples that show how these two mechanisms work. In each of these panels, I'm showing you the evolution of a certain quantity with redshift. So redshift 2, where I picked the galaxy out, is over here on the left. And in each panel there are two lines. The blue line is the individual galaxy that we're looking at, and the black line is, for comparison, the average evolution of all of the galaxies, which end up with a few times 10 to the 11 solar masses at redshift 2. So they end up at the same mass range. Now, if we look at the stellar mass evolution of this galaxy, we see that it is undermassive for most of its lifetime and catches up really quickly around redshift 2.5. Unsurprisingly, this is accompanied by a huge burst in the star formation rate. Even though it's been sort of underperforming up until then, we've got a big spike here. And this is not a coincidence. It doesn't happen out of nowhere. It happens at the same time that the galaxy undergoes a major merger. If we look at the central density, so this is the stellar mass density in the central kiloparsec of the galaxy, at the same time, this density jumps by almost 2 orders of magnitude, which tells you that the star formation is very centrally concentrated. And so we also see a decrease in the stellar half-mass radius at that time, not because the galaxy is physically shrinking, but because I'm producing a lot of stars in the center, which drives down the size of that sphere that contains half of the star. And so when we put all this together, this tells us a story where a major gas-rich merger drove a lot of gas to the center of the galaxy through tidal torques and provoked an intense and centralized burst of star formation that resulted in a compact merger remnant and got it into my compact category right under the gun, right before redshift 2. All right, in this second example, it looks very different. Recall that in the example I just showed you, the galaxy was undermassive for most of its lifetime. In this case, the galaxy has been overmassive and formed very quickly, quenching around redshift 4. When you look at the star formation rate, you see the star formation rates were very high, quenches around that time. And this galaxy has always been extremely dense. When we look at the central density here, we can see that around redshift 6, the central density is comparable at this time to the central density of a more massive galaxy later on. And so because the galaxy has always been very dense, it has also always been very small. So it formed at sub-kiloparsec sizes and was able to maintain that size after quenching. Nothing happened to it, just sat around until I came along and picked it up at redshift 2. So in this case, the galaxy owes its compactness not to some extreme star formation burst event, but rather simply to the fact that it formed at a very early time in the universe's history. When the scale factor was very small, everything is very dense, and so it naturally forms with a smaller size at that early time. And then it manages to hang around with nothing happening to it until I come along. So we have two very distinct ways of producing a compact galaxy at redshift 2 here. Now when I look at my full sample of 14, I've colored the points here according to which formation mechanism was dominant for them, with the red ones being the early formers and the blue ones having one of these starburst events. The two are not mutually exclusive. Some galaxies do sort of form early but then also have a starburst event later on. I just picked the one that was sort of dominant for them. And out of the 14, about a third of them are these early formers, and 2/3 are these central starbursts. When you go to redshift 4 and ask where their progenitors are, for example, you can see that for the most part, these early forming guys are already in place, whereas some of the starburst ones have yet to undergo whatever event drives them into that region. Now, of course, we can also ask the reverse question. We've asked where do they come from, now we want to know where do they go, what happens to them, and where should we be looking in the local universe for them. Now I'm changing my criterion for compactness a little bit here to make it more similar to the way that the observers talk about compactness. Now what I'm doing is I'm drawing a line across the mass size plane here on this sigma 1.5, which is sort of a surface density criterion. And because I've sort of shifted my criterion up a little bit on the higher mass end, it also increases my sample size. So the punchline answer to the question, what do these galaxies become at low redshift, is that they become everything. In the intervening 10 gigayears between redshift 2 and redshift 0, some of these galaxies gain almost no stellar mass, and some of them gain an order of magnitude in stellar mass, and they really spread out over this whole massive galaxy sequence. All right, so where does the stellar mass come from? Here I'm showing you the relative change in stellar mass, so it's how much mass did this galaxy gain between redshift 2 and redshift 0 relative to its original redshift 2 mass. Up here are galaxies which gain, the ones which gained, you know, an order of magnitude. Down here are the ones that hardly changed. You can see there's a lot here in the middle which grew by factors of a few. Down up here, this panel is an inset, which shows you these guys down here just in a different range, going from -1 to 1 instead of 0 to 15. And this change in stellar mass could be due to any number of things. You can gain stellar mass by forming your own stars in-house, in situ. You can gain stellar mass by picking it up off of other objects through mergers or stripping or something like that. You can lose stellar mass just because of the fact that stars evolve and explode. And you can lose stellar mass through stripping. Now, if I split this up now and I look just at what is the contribution to this change in mass from stars which are formed ex situ, stars which were acquired through mergers, you see that we get almost exactly the same plot here. You can only really tell the difference down here at the low mass end. And so what this is telling you is that for almost all these galaxies, the change in mass is almost entirely due to the addition of ex situ stars, stars which are not formed in that galaxy. There is some contribution from these other effects as well. These panels now I'm putting on the same scale as the inset, not the overall larger panel. This being the amount of stars which were formed in situ, you can get up to maybe 20% more stars. This is the decrease from stellar evolution, so you lose about 15%. And this is the decrease from stripping. So there are a number of galaxies here which were heavily affected by stripping, most noticeably this one. But by and large, the ex situ stars are really what's getting you there. All right. So now,
Sorry.
yeah. Go for it.
How is this consistent with the poster child that you showed where, you know, basically there was just this burst of star formation in the core that you started out with? How is this consistent?
Right, okay, so this is a slightly different question now. So now I'm saying, given that it is compact at redshift 2,
What happens
how is it
after?
evolving after that? Yeah.
And there's no pre-post correlation necessarily.
No, there's a slight, well, okay, ask me again later
Okay.
on. I looked and I only found a very small trend. Yeah.
So stellar evolution produces, and a lot of that goes into the gas. And is that what then fuels the in situ star formation?
Yeah,
Or if not, where does the gas go? Does it just get heated up? Does it stick around?
Yeah.
Do you have an idea about that?
Well, it does get, ejected,
Right.
right, through both through air and through stellar winds. So it does have some, momentum and energy, which is going to try to throw it away from the galaxy.
Right, just
Certainly some of
big.
it sticks around,
Yeah.
and does recycle back in a little bit. But I haven't done a detailed, tracing of where the gas goes. All right, so the next question that I want to look at is, where are these old and new stars situated within the descendant galaxy? So now what I'm showing you are postage stamps of the eventual redshift 2 descendants, where I've used sort of a weird color bar that has two axes. So light to dark now is the stellar surface density, so these dark regions are the dense core of the descendant, and the color tells you something about where the stars from the compact galaxy are dominating. So specifically, the color in a given pixel tells you what fraction of the stars along the line of sight were present in the original compact galaxy. And I've ordered the galaxies here by their descendant mass, so you see a general gradient going from blue to red. That's because these galaxies are comprised almost entirely of the same stars from redshift 2, and these galaxies are dominated by other stars. And so you can see in a lot of cases, there's sort of a color gradient going from red on the inside to blue on the outside, which tells you that the stars from the compact galaxy are dominating the core of their redshift 0 descendant. There's also a couple of other cute morphologies here that we can pick out. But let's look at in detail how they got this way. If we start up here at the high mass end, here's a galaxy which looks very blue. And it's hard to tell, what exactly happened to the compact galaxy at all. I can see, maybe you can see, that there's a thin band of green going across the middle of the image here. And so what you might guess happened is that the compact galaxy encountered a more massive galaxy and was disrupted in a merger, so that this green band here traces out the orbital plane on which its stellar contents were scattered. If we look at the mass evolution of the compact galaxy, this is time now, so time goes this way. We can see that this is exactly what happens. This black line here shows the mass of the compact galaxy. There's a big jump here around 9 gigayears, where it merges with another galaxy here, which I've shown with a dashed line. Now here I'm showing images, each of which correspond to one of these big gray points on the mass plot there. And when we look at these images, we can see this story very straightforwardly. This galaxy is sort of minding its own business, starts falling into the potential well of a more massive galaxy, gets completely disrupted in a merger, and settles into this little plane. So its identity has been effectively erased from the galaxy population. We can also see what happens to the radius in the same way. See the same sort of jump here when it joins the merger tree of the other galaxy. There's another line here, this red line, which shows you the half-mass radius of just the stars from the compact galaxy. There's a big jump here as well because these stars are just getting scattered all over the place. So that half-mass radius increases also.
So,
Yeah.
This is a really interesting example. So, because if you have a lower mass galaxy that becomes quiescent and compact, in the vicinity of one, but I guess just keeps forming stars
Yeah.
at the next sort of half Hubble time or something.
Yeah, you can see they were not so dissimilar, but this guy kept going.
I mean, can you tell what caused the one to
Why one
compact?
quenches and one doesn't?
Right. Not just quench, but become compact at the same time, right? But the half-life radiator, about factor 2-ish as well.
Yeah, exactly. Well, it does seem, both observationally and in the simulation, like there is a connection between compactness and quenching.
Right.
In that compact galaxies seem to, or it seems like perhaps galaxies quench when they reach a compactness threshold. Sort of.
I would tell why this particular galaxy. I mean, if anything, I would have thought it'd be the other way around with a more massive, would have ended up having more central surface stellar density to hit compactness. But you're saying.
Yeah, I mean, I guess
arbitrary.
it's just more spread,
Okay.
spread out, yeah.
Yeah, that's a great point. Look at that there. It's a really interesting example.
All right, so in this case, this compact galaxy is basically gone. If we move a little bit further down, we see one of these cases where we have a color gradient. The mass evolution here is a little bit more gentle, but the galaxy does undergo 2 major mergers. These are about 3 to 4 mergers, which is pretty major, but it does remain the main branch of the merger tree throughout. And when we look at the images now, we can see that the reverse is happening in this case. Rather than the compact galaxy being disrupted, it is doing the disrupting. So here, the galaxy had encounters with 2 galaxies which were of similar mass, but certainly lesser binding energy. And so it was able to effectively disrupt these galaxies and accrete their stellar contents onto the outskirts so that it creates this envelope of ex situ stars on the outside and gains a lot of stellar mass in the process. And when we look at the evolution in size, you can see that during these mergers, the overall size of the galaxy inflates a lot, but the size of just the stars from the compact galaxy hardly changes at all because it's just minding its own business here as the core of its descendant. Now here's an example where the picture appears essentially uniformly green. When we look at the mass evolution, you can see it was minding its own business for a long time and then had a 1-to-1 major merger around 12.5 gigayears or so. When you look at the images, you can see what a really equal merger this was. So these 2 galaxies were very equal not only in mass but also in binding energy. And so they were able to really thoroughly mix their stars together so that you get this uniformly green appearance later on when I pick it up at redshift 0. And again, we see very little evolution in size, and then an increase in both the overall and compact half-mass radius because it was disrupted somewhat in this merger. And of course, when we move all the way down here, when we see a galaxy that looks mostly red, you can imagine what this is going to look like. Not very much. This galaxy is boring to look at, but interesting to think about, because 10 gigayears is a long time for nothing to happen. And there are a few galaxies down here like this. All right, I've shown you a few examples, told you a few stories of the types of things that can happen to these galaxies between redshift 2 and redshift 0, but how do we quantify this and talk about how common these types of evolutionary paths are? Well, one way to do that is to look at the cumulative stellar mass profiles. What I'm showing you here is the enclosed stellar mass at a given radius with 2 lines here, the black line which shows the enclosed mass of all stars, and the red line which shows the enclosed mass of just the stars from the compact galaxy again. And you see a very different relationship between the red and black lines for each of these 4 stories. The ratio between the lines here is large at all radii, when the compact galaxy was consumed, effectively 1 at all radii here where it's just been sitting around, sort of middling in this mixed case. And in the case where the compact galaxy is the core of its descendant, the ratio is effectively 1 at inner radii and higher at outer radii. So we can use the ratio between the red and black lines at an inner and outer radius to sort all of these descendants into these categories. And when I do that, I get something that looks like this, where out of the 35 galaxies that I started with, 5 of them were consumed in a merger with another galaxy. 17 of them, which is about half, exist as the core of a more massive descendant. 2 of them are these mixed galaxies, and 11 of them, which is about a third, survive more or less undisturbed. Now, if you have good eyes, you may notice that the number that I wrote there and the number of points you can count is not the same. That's because a single galaxy at redshift 0 can have more than 1 compact progenitor if they merge together. And in fact, the only way that we could get this equal of a merger to get this mixed case was that the 2 galaxies that merged were both descendants of compact galaxies. So these 2 combine to become this 1 green point. And so the most dominant evolutionary pathway for these galaxies is for them to accrete all these ex situ stars on the outskirts and to exist as the dense core of a more massive descendant, but it's by no means the only story. Now we can also ask, do we have any sort of predictive power? Can we tell at all what sort of evolutionary path one of these galaxies might make. And one thing that we might look at is environment. Here now I'm showing you the ratio between the descendant and progenitor masses on the x-axis and the size on the y-axis, with the color indicating the category that I just showed you in the last panel, so that the galaxies which gain a lot of mass and size are these consumed guys, and the galaxies which did not gain very much mass and size are these undisturbed ones. There are also a couple of different symbols that I'm using. A square here indicates that the compact galaxy is not on the main branch of its descendants merger tree, so it's not the primary progenitor of its descendant. And a triangle here indicates that the galaxy is a satellite at redshift 0. The rest of them are centrals. Now, if I take away this coloring and instead color the points by the number of mergers that it underwent between redshift 2 and redshift 0, you can see a gradient here where, unsurprisingly, the ones that managed to survive undisturbed underwent very few mergers, 0 or 1, and the more mergers you have, the more mass you gain, and the farther you move up this track. If I take the mergers away and replace it with an environmental statistic, you can see the same sort of trend here. So now the color indicates the distance to the 5th nearest neighbor at redshift 2, with blue being a small distance, so that's a dense environment, and red being a large distance, so it's a sparse environment. And again, you can see these galaxies which didn't gain very much mass are almost uniformly red. So they live in very sparse environments, and this is how they can avoid mergers and avoid gaining mass during that whole 10 gigayears. There are a couple of exceptions here, which are these sort of light blue-looking triangles. Remember, a triangle means that it's a satellite. So this is a galaxy which is a satellite in a larger cluster, and both of these types of galaxies are protected from mergers. In this case, because it's in a sparse environment with nothing really around to merge with, and in this case, because it lives in a cluster with such high orbital velocities that it's difficult to merge. So if we want to find descendants of these types of galaxies in the local universe, this is where we should be looking, either in very sparse environments or in very dense environments.
I had a question.
Yes?
So on the right-hand side, I guess it's the third square down on the right-hand side, they have, it lives in a dense environment, and then in the middle panel it's had 0 or 1 mergers. It's hard
Yeah.
to describe.
So
Yeah, that guy.
for these ones, because for the squares, the counting of mergers gets a little weird. Basically, the only mergers that I counted here were the mergers that it had before the big merger, where it joined this really massive galaxy. So in this case, this red one is probably just because it got eaten pretty fast, so it didn't have time to do a lot of merging. So in both of these cases, taking this population of galaxies at redshift 2, which have very similar properties, looking forwards and looking backwards, we can see that the galaxies spread out a lot and can follow a lot of different kinds of evolutionary pathways. So I want to talk a little bit about what this means in the context of observational methods for trying to predict galaxy progenitors and descendants. In particular, this approach of using a constant cumulative number density to trace galaxy populations across time. So what we're looking at here are mass functions, cumulative mass functions. So at a given mass, this tells you the number density of galaxies which have at least that much mass. So it's higher at lower masses. There are a couple of different redshifts here going from redshift 0, 1, 2, 3, 4, 5, 6. These are mass functions from Illustris. And the idea with this method is to find the number density of a galaxy at a given mass at redshift 0, for example, and then use that number density to predict the masses at other redshifts. Now there are a couple of assumptions that we need to make in order to do this. If we assume that galaxies preserve their rank order in time, meaning that if galaxy A is more massive than galaxy B at one redshift, they will evolve like this and not like this, and won't cross each other. And if we assume that mergers are negligible, because what will happen with their mergers is that you'll remove something from the population and everything shifts up one in rank. If we make these two assumptions, then this assumption of a constant cumulative number density is valid. And so you can make a prediction about the mass evolution of this population. And this is a fairly commonly used technique. But based on what I've shown you thus far, neither of these assumptions is really valid, at least certainly not at the high mass end. And so what happens is that you get a slightly, the prediction that you get from using this method is slightly different from the actual underlying reality, at least in the simulation. So here are a couple of evolutionary pathways that you get. This red line shows what happens for Milky Way mass galaxies at redshift 0. We're trying to predict their progenitors. This is mass against redshift and number density against redshift. If we make this constant number density assumption here, using the illustrious mass functions, you can predict a mass evolution for these Milky Way type galaxies. But if we go in the simulation and we actually take a hold of the galaxies in this bin and we trace them backwards in time, you get this blue line here, where the line in the middle here is the median, and this fanning out here shows you the distribution of the galaxy masses that you actually get. So you do get an overall evolution in the cumulative number density of this galaxy population. So there are two problems here, one of which is that there's a systematic offset between these two lines, and the other of which is that there is an enormous scatter in the masses and number densities of these objects. And so if you're trying to predict the median evolution, you can correct for it somewhat by fixing this offset, but depending on what question you're trying to ask, if you follow this red line, the number of actual progenitors that you're going to be picking up here is very small. And so it's hard to use this population to predict what's going on with this population. So this is a bummer, to say. But I think we can improve it somewhat. All right, what I'm showing you now is this gray histogram here shows you the masses of the progenitors at redshift 2 of galaxies which had 10 to the 11 solar masses and stars at redshift 0. So I took a sample of 10 to the 11 solar mass galaxies, traced them back to redshift 2. This is the distribution in stellar mass that you get for those progenitors. Now this red histogram is the prediction that you would get from assuming a constant number density. This is not due so hot. This overlap here is maybe 10% of the distribution. You can, again, improve this somewhat if you allow that number density to evolve. You can at least track the middle of the distribution. But you can do a lot better if you not only allow the number density to evolve, but you allow it to be the center of a distribution, rather than having a fixed bin in number density. Now, in order to make these predictions, you need a function for how the number density evolution occurs with time. You also need a function for the width of the distribution as a function of number density and redshift. And in order to get between number density and mass, you need mass functions. Here I'm using everything from illustrious. And of course, by construction, this is going to give me a better outcome. But these functions can equally well be applied to observational data. When we do these fits for n as a function of all these things and sigma as a function of all these things, these functions are actually surprisingly consistent, not only across different methods of doing this. So we've measured these functions. Peter Baruzzi has measured this function in his semi-analytical models. It's been measured a number of times, and actually these come out pretty similar across all these methods. Not only that, but we've measured this function for a number of different quantities. So I showed you the evolution in number density when mass, stellar mass, is used to assign the rank order. You can do a similar exercise by using the dark matter halo mass to assign rank order or velocity dispersion. And surprisingly, you actually get the same evolution and number density, even when you use different rank ordering properties. This was pretty surprising when we first realized this. But I think what this means is that the evolution in number density is really fundamentally driven by the dark matter halos. It's driven by lambda CDM, and the scatter in these other properties is coming from the scatter in halo mass. So because these appear to be fundamental, we can pretty directly apply them to observational data as well. So instead of using the mass functions from Illustris, I can use mass functions from observations and make the same kind of predictions using observational data. So here, for example, I'm using the mass functions from ZForge to make the same prediction. Galaxies with 10 to the 11 solar masses at redshift 0, what do they look like at redshift 2? And these are the various predictions that you get for all of these methods. And again, you get a very different set of predictions when you allow the number density to evolve and when you allow it to be a distribution rather than a fixed bin. Now, this distribution in mass, or this changed prediction for the mass, is also going to manifest as a change in your prediction for other quantities when the mass is what you're using to select galaxies out of a sample. So here again, I'm looking at redshift 2, 10 to the 11 solar mass galaxies. If I with stellar mass on the x-axis and size on the y-axis, if I follow them forward in time, as we've seen before, you see them disperse all over the place. And if we make a prediction for galaxy sizes, using a constant number density assumption, and using some size mass distributions that I measured from Illustris, this is the prediction you get for where these galaxies should lie in this plane. If you, again, allow the number density to evolve, you put it there. But if you allow the number density to be in some distribution, you get a contour that looks more like this. And so we're more effectively capturing the behavior of the entire population. And again, I don't need to be using the Illustris mass functions and the Illustris size mass distributions. In fact, you should not, because both of these have some problems. I can use just purely observational data. So now again, I'm using the mass functions from ZForge and the size mass distributions from Candles, and you can make the same sort of prediction using observational data and these two functions. And this different distribution in mass manifests as different distributions in sizes. So if we really want to be trying to capture how populations of galaxies evolve, I think this is a better way to do it. Now, just one more example. Let me bring it back to the Milky Way progenitors. I showed a plot like this earlier on. This shows the predictions that you get from Milky Way mass galaxies at redshift 0, their progenitors at higher redshifts. This is the constant number density line. This is the evolving number density line. There are two lines here for each method, one of which shows the median evolution within the sample that you get from this prediction, and one of which shows the mean. So the solid here is the mean, the dashed line is the median. The black line is, again, from Illustris, the actual progenitors' black lines, so mean and median. The actual evolution of the progenitors, and the green is the prediction that I get from allowing there to be a distribution in number density. And so if you do just the evolving number density, you can actually pretty well capture the median evolution, but you're losing the spread, so you don't continue to track, the overall sample, and you miss out on the mean behavior as opposed to the median behavior. And so this is all sort of by construction because of the way that we constructed these number density evolution functions, but it applies equally well to other quantities here. So here's the mean and median star formation rate of this population, these predicted populations that you get from all of these methods, with again here being the constant number density assumptions, which overshoots it because you've predicted the wrong masses. Blue, evolving number density, which again captures the median behavior, and green being this distribution in number density. So my point is that if we face up to the fact that populations of galaxies diffuse out in mass and in number density. And we stop talking about the typical progenitor or descendant, but start talking in language like the median or the distribution of a galaxy progenitors or descendants. We can start making better predictions, I think, of how galaxies evolve over time. All right, so just to summarize, I started off talking about these compact elliptical galaxies in Illustris, picking them out of redshift 2 and following them backwards and forwards in time. The compactness that I find at redshift 2 is driven either by a centralized intense burst of star formation or by an early formation time. When I trace them forward to redshift 0, I find that about half of the compact galaxies exist as the core of a more massive descendant. About a third of them survive undisturbed, and the remaining few are mixed or consumed in major mergers and disappear from the galaxy populations. And these results show that the progenitors and descendants disperse widely in stellar mass and experience a variety of evolutionary paths, which implies that if we want to try to observationally connect galaxies populations across redshifts, we need to start talking about distributions. All right, thanks.
Plenty of time for questions. Go.
I wanted to ask this at the beginning, but you had momentum, so I didn't want to, have the race start again. Your simulation goes from like redshift of 127 to
Yeah.
the present, okay? And when people that work on this, the distance coordinate, this is co-moving coordinates? Because the universe is expanding
Yes,
a lot,
yes,
right?
yes,
You know,
yes.
and so if we talk about a box of a particular characteristic size,
Right. Yes.
the
So
length of that, the size of that
100
box
megaparsecs,
changes.
The 100 megaparsecs
Yeah.
is a co-moving volume.
Okay.
Yeah, so the box basically
Yeah,
expands
okay.
as the universe does. Yeah.
Yeah, but you normally divide out A is divided by the
Yeah,
scale factor.
whenever I talk about kiloparsecs in the talk, I've converted it to physical sizes, but the simulation does take care of that.
Other question? I'm gonna ask another one. So, the different descendants of the core, so these are the compact elliptical galaxies. It must transit some kind of observational signature you could make of redshift 0. I know Jenny Green, for example, did a bunch of these alpha over iron gradients, or abundance of gradients in present-day ellipticals from Sloan, showing it's basically consistent with what I think is the dominant mode here, where you build up the weights of these galaxies with minor mergers.
Yeah.
I mean, do you guys reproduce that? Do you trace those kind of abundance factors?
Yeah, so I personally haven't done a lot of work with the metallicities. There is a student, Ben Cook, who has been working on metallicities, and he's shown something recently that does show how the alpha abundances, the slope of the, how that changes depending on the merger history of the galaxies, showing that it does get shallower when you're more merger dominated on the outskirts. So I would assume that we should be seeing that as well. Yeah, but metallicities are tricky.
Yeah, all right. But observationally too. So.
Yeah.
I'm going to ask a bunch more questions. Maybe also. All right, I'm going to keep going. So some of them, if I took it away correctly, which I think I did, is that you have a compact quiescent galaxy at redshift 0. So the ones that sort of survive on graphs down to redshift 0. Are those predominantly in these cluster environments? I mean, I think that's where people claim
That's
to
where
find
people
them.
have found them.
Right. Like Volcani papers.
Yeah, I don't remember exactly.
People look for these things. Right?
Yeah.
Because I always wondered if it's the tail of the distribution, you just find them more preferentially in clusters.
Yeah, there's observationally, there's actually opposing claims. Some people say they're in clusters, some people say they aren't. I think some of Janelle's compact galaxies, they're like half and half.
There are a lot of them actually in clusters.
They're kind of, does it kind of follow what the simulations are showing?
Well, I mean, I'm studying the whole acid.
Yeah.
Yeah, I mean, I have to think, so I'll
Yeah.
ask my question.
There's also a cloning bias here, which is that I'm just looking at the galaxies which were compact in redshift 2 and where they ended up, rather than like where all the compact galaxies that were ever ended up, which are two slightly different questions. So I think there's some idea that in clusters, actually you can produce more compact galaxies by stripping.
Right.
Which is a totally different sort of question. But yes, based on.
Some theories do go down in mass.
Yes,
That's
so there's
kind of
one
consistent
actually,
with that, yeah.
that one
Like, you have
guy.
that like drops by a factor of
That
2.
one guy that lost 60% of its mass
Yeah.
is just like a crazy person. It just,
I think you should,
it
it's
like
all
dives
stripping.
through this
Okay.
halo and it's really stripped and it's like coming out the other side around to zero.
So it's left at the core after it's been,
Yeah.
I guess, evaporated away or something.
Yes, so that seems like a plausible way to continue forming them at lower redshift.
Okay.
So I would expect to see them in clusters certainly, but I would also expect to see them in voids. But I don't know if people look there.
I would ask one more thing about the progenitor descendant stuff,
Yeah.
because I think you're on the right track here. I mean, that scatters was always kind of confused and confounded us. You know, the one plot comparing the mass evolution from Peter Madoc's paper, my paper, and then your distribution plot. Yeah, right. So this, I want to clarify, this is showing the mass evolution from the, basically mass, no, those are the actual distribution of descendant masses
The blue is the
from
actual,
lustrous.
yes,
Compared to our measured ones.
yes.
Because it took me back, I was like, well, how can we do such a good job with like the median?
Well, so
But at the
you,
end- but I think
didn't you
at the
use
end-
Peter Baruzzi's,
Right, which are based
Yeah.
on the measured stellar mass functions.
yes, so the
Right.
whole idea here is that,
'Cause I think
because
it's-
you use Peter Baruzzi's,
Right, so the evolved
predictions,
number
you're gonna
density.
get something
Right. We
similar.
knew that was better than the constant approach, which is what more like what Peter did. But at the
Right.
end, we always end up with your 80th percentile, and it dawned on me, well, that's probably this Eddington biasing we're talking about. The observed mass function can lead you to see that evolution, whereas you're seeing the true evolution in those simulations. It's something we can talk about later.
Yeah.
I think I can explain.
are you talking about this?
Yeah, just the offset.
I think this is actually because the illustrious mass functions are not the right shape.
Well, I don't know if the observation was the right
Yeah.
shape, so we can debate about that. You don't trust your theory, I don't trust my observations.
Okay,
and we'll
sounds good.
Figure out what the truth is later. Any other questions or comments?
A very technical thing.
Mhm.
But, so you were showing the difference between the mean and the median.
Yeah,
For the mean, they're going to be very different if you're doing the mean of the log. or
yes,
the log
I
of
know,
the
I
mean.
know. I did the mean of the linear, which is why, I mean, if I did the mean of the log, it would come out the same as the
Yeah,
median.
yeah, that's what I was saying.
Yeah.
Too
But
much.
people, I mean, this is what people do though,
Oh, yeah.
so
Yeah, no, you're right.
I sort of somewhat did this on purpose to mimic one of Peter Van Docken's papers.
Sure.
Yeah.
And then so like, you come up with nice distributions, like it's basically you're just waiting. This is,
Yeah.
the way I like this is
That's-
because you're getting around this problem of if you have a galaxy of a given mass, what track does it take? Where you say you don't know, you just know what the distribution is.
Yeah, so
Or you can-
essentially what the code that I've written does is that it assigns individual galaxies probabilities of being a progenitor.
Right.
And then these are weighted medians and weighted means for like all of the
Right,
galaxies.
so a galaxy can be a weighted progenitor of multiple paths.
Yeah.
We use that sort of- All right, I'm excited by that. Anybody else want to ask for anything else?
Actually, the most reason I'm misunderstanding, what's the difference here between like running that and just like a bunch of different merger trees? Like,
What do you mean running a bunch of different
so,
galaxies?
I think you're saying why bother with the, because the. she
so
said
this distribution you're talking about is encoded in the fact that there's some distribution of merger trees that.
Mhm.
Yeah, and I think
is
the
this
hydro, so it's taking the stochasticity of the.
Yeah.
of
Yeah,
the
so
star
it's
formation.
partially driven by the stochasticity of merging and partially driven by the stochasticity of star formation.
Okay, so you're,
Yeah.
okay, so star formation, that's not in merger trees.
Right.
It's not properly,
So
right?
we're, like Peter Baruzzi's stuff is n-body simulations combined with observed stellar mass functions, and then he works in Bayesian magic to get the whatever the stellar mass, halo mass relation is, and you can trace them that way.
Mhm.
They call it a sham, which I was
Yeah,
stellar
yeah.
mass, halo mass, abundance matching.
Yeah, okay,
Right.
so,
So that's
okay,
the difference, but I understand it, right.
Okay, so let's say, so hypothetically, right, if you ran like a bunch of merger trees with a bunch of universes with all some baryonic magic in there somehow, like, your distribution would encode all these
Right.
universes that are plausible in some way. Is this kind of what you're theoretically encapsulating when you measure these probability distributions?
Essentially, yes, except I'm not sure that you need a bunch of different universes. You just
Okay.
need a really big box of one universe.
Yeah,
But
okay.
yes,
She's got a bunch of Milky Ways
yeah.
at present,
Oh, okay,
she's
okay.
saying, so, right,
Yes,
how many,
right.
1,000 or something?
Oh, it's gotta be at least, yeah.
Yeah, okay, you're right. So if you're talking about like the progenitor of one galaxy, okay.
Right.
So we don't need like top of ensembles, okay.
Yeah.
Okay. So this is all like encapsulated. Let's say if you knew like the physics of the whole universe and how it operated, like the CDM, star formation, feedback, etc., then you can then there's some fundamental distribution that
Right.
each galaxy obeys
Yes.
that you're from.
Right.
Any last questions? Before we say thank you, there is grad student time scheduled. When is harassment? We call it grad student harassment. Egress. We don't know which way the vector points. You figure that out.
Well, I'm also a grad student.
Yeah, that is good. No matter which way the arrow points, someone will be harassed. That's at 3:30. Okay, I'll trust that. Otherwise, Sarah's around all day today and tomorrow, so please find her and talk to her if you want to know more. Thank you very much. Distribution. That's the way to do it.
So this physics, so it's all in like some merger tree with various